Hello students, this is the second lecture in module 1. In the previous lecture, we just started looking at what the compiler does and what the assembler does, and in to understand them we also uh, got introduced to the terms called assembly language and machine language, which is basically a sequence of zeros and ones. Post that, we looked at the five basic components of computer, and then uh, we started looking at the memory module and wanted to understand how information is stored in it. So von Neumann architecture says both the program and the data on which the program would work, both will be stored in the memory, and they will be retrieved to or brought to the CPU whenever they are required. In the process, we also got introduced to the terms called word, byte addressability, and word alignment. Continuing the discussion further, the to understand how a byte of data is stored in a word. For example, let's say our word is group of 4 bytes. Now, if I am writing a byte of a data, where is it stored? Because the word is the unit of interaction between the CPU and the memory. Each byte in the word has its own unique address. So to understand that point, there are predominantly two types of assignments. Uh, One is big endian and another is little endian. In the big endian, the lower byte addresses are used to store the most significant bytes of the word. And in the little endian, we do the exactly opposite thing. The lower byte addresses are used for the less significant bytes of the word. So to understand this, let's look at an example. In the picture shown here, on the left side you have the big endian assignment, wherein the byte addresses are, let's say, the word in the word address 0, the byte address 0, 1, 2, 3 are arranged this way, and in the second word, which whose address is 4, the bytes addresses would be 4, 5, 6, 7. Right. On the other hand, to the right, you see the little endian assignment, where the byte addresses started not from 0 to 3, rather from 3 to 0. Okay. Now, let's take an example. Let's say we want to store uh, an a word of data which is 4 bytes, uh, 0A, 0B, 0C, 0D. It's in hexadecimal form in a location which is having the address 0. So in the big endian assignment, these these data are written such a way that the most significant bytes of the word, here 0A is the most significant word, sorry, most significant byte, it would be assigned to the lower byte addresses. So in the word address which is starting with the word address 0, the lowest byte address is 0. So 0A is written in location 0. In the same way, 0B is written in 1, 0C in 2, and in the third byte, the byte with address 3, the last value 0D is stored. On the other hand, in the little endian assignment, the lower byte addresses, which is again 0 here, would be storing the least significant bytes of the word. So the least significant byte here is 0D. After that, in the location given by byte 1, we are going to store 0C, 0B, and 0A. Now, we in both these assignments, whether it is big endian or little endian, you see that 0A, 0B, 0C, 0D is stored in the same way. That was the way the textbook explains. But to avoid any confusion, if we want to follow the same addressing, let's say this is my word 0, byte 0 is the leftmost, followed by 1, 2, and 3. And if, with this locations, if we want to follow little endian, then 0D is stored in byte 0, 0C is stored in byte 1, 0C, B is stored in byte 2, and 0A is stored in byte 3. That's what the little endian assignment would say. To avoid confusion, you can stick to the address, labeling of the addresses of one of them, and then you can understand how the data will be written. Okay, so this big endian and little endian, like I mentioned before, help us to visualize how the data is stored within a word. Now, which of these should we choose when we want to build a computer, and why should we go for it? So there are uh, pros and cons for both of them. In fact, there are some hybrid approaches also. At this juncture, there is no specific motivation to go for one over other. So to quickly relate to and understand this point, let's see what we let's understand what we do when we are given, let's say, a textbook. For example, we read from left to right. So in that way, we are kind of following the big endian assignment, you can say, because that's the way we would uh, interpret a word of information also. But when, let's say, we are given two numbers to add, we start from right to left, isn't it? So we start from the lowest digit and calculate the carry and move to more towards the left. So in the same way, there is no hard and fast rule that only big endian needs to be used or only little endian needs to be used, and that one is greatly better over other. There's nothing like that. So we in many of the current systems, you see a mixture of them, and there is no specific winner here. There is no primarily discussion in this case, right? Both are equally relevant. Following that, let's look at the processor memory interface with what all we have discussed so far. Uh, we For simplicity, I'm just considering the memory module and the processor module, which has the data path and the control path. We have seen that there would be some additional registers which will quickly supply the data to the ALU based on the control signals generated by the control unit. And in addition, we also have some special purpose registers which are program counter or instruction register. So to interact with the memory, we can assume that there is a dedicated processor memory interface which can primarily have two registers again. MAR stands for memory address register and MDR stands for memory data register. Now, when the control unit signals the memory unit to supply some data, it needs to give an address. So that address will be placed in MAR. The memory would consume that address, get the value and write it to MDR. So the value from MDR will be either directly written to the registers or processed at the ALU based on the implementation. Now, if you want to write some data to the memory, so what the control unit does is it places the address and the value that needs to be written in that address in MAR and MDR respectively. So in that way, the memory and the processor or CPU interact. So PC is sometimes also called as IP. It means that it is an instruction pointer. If you have forgotten what PC or IP do, is it they point to the instruction that will be executed next. Okay, and IR is the instruction register, which is storing the actual instruction that is currently under execution. So even though we have these MAR, MDR, PC, IR, etc., none of these are visible to the compiler. Only the registers R0 to Rn-1, which are also called architectural registers, are typically visible to the compiler. So when the compiler is trying to generate the assembly program, it will use these registers. We are going to understand how it does in the future classes. Moving on, here when we are talking about the compiler and the assembler and the very notion of instructions, understanding what instruction set architecture means is one of the basic things that we should do. What ISA does, or what it basically is, it's like an agreement between the hardware and software. The hardware would say that it would build it would have all the components and connections, etc., etc., following an ISA. And the software says, okay, I have this ISA, I'm going to build my software which will be compatible with this ISA. Okay, so it's more like an agreement. And to quickly port to the great ideas of computer architecture, this is a layer of abstraction between the software and hardware. What all it contains is all the information that is necessary to convert a high level program to a machine level program, or in the machine language, that will run correctly on some particular hardware. What ISA in general provides is the different types of registers that are present and how many of each type of those registers are present in the hardware. Then the data types at the hardware. We'll see what the data types are, but to quickly understand, they are analogous to our data types at the HLL, like int, long, double, unsigned, etc. Right? So in addition, ISO also gives us information about the instructions that are supported by the hardware. So it would give us information like whether 32-bit multiplication is available or not, whether uh, division operation is available or not, or any other complex operation, let's say something like convolution is available or not, or multiply and store, MAC, you can say. Those kind of operations are available or not, on left shift, right shift, etc. All these, which of these instructions are there, and what width they support. All this information is given in the ISA. In addition, it also provides addressing modes. Addressing modes help us to give the address for the data that we want to perform some operation on. Let's say you want to add two numbers. Now, how do you give those two numbers? Whether you can give the numbers directly, or you can give the address of those numbers only, or you can give address for one and probably the value of another one readily available. So many options will be there, and that information is given by the addressing mode. Another important aspect that is given by the ISA is instruction encoding. This information will be used by the assembler to convert an assembly instruction to a machine instruction. So we are going to see all these aspects in this module, considering one particular ISA, which is RISC-V. Moving on, there are two different types of ISAs, RISC and CISC. RISC stands for Reduced Instruction Set Computers, and CISC stands for Complex Instruction Set Computers. Now, as the name says, Reduced Instruction Set Computers has very simple instructions. It follows the load store architecture or the von Neumann architecture. What it means is the memory operands are accessible only through some specialized instructions which are called load and store instructions. Either we can load the data from memory or we can store the data to the memory using these instructions. All the operands that we use in the arithmetic and logic instructions are either in the registers, or maybe at most one of those operands can be given as part of the instruction itself, but that is the limit. In addition, there is a strict constraint with the RISC ISA that the size of one instruction need to be at uh, one word, nothing more than that. So if let's say our memory has the word size of 64 bits, then each instruction can be maximum of 64 bit. If the memory word size is 16 bit, then each instruction would be of 16-bit size only in the RISC ISA. Coming to the CISC ISA, as the name says, not only the simple instructions but some complex instructions can also be present in this kind of ISA. And it has flexibility that the size of one instruction can span multiple words. And it also has flexibility that we can perform arithmetic and logic operations on two data items which are in the memory. Unlike the RISC ISA where we expect the data items to be available in the registers, here we can directly operate on data which is in the memory. Of course, we need to get them to the processor and write back the result back to the memory. All this will be performed by one single instruction itself. So let's look at an example. Let's say that we want to perform an operation b plus c and write it to a variable a. Let's see how the RISC and CISC ISAs would convert this simple operation into appropriate assembly language. Okay. Now, the very first thing in RISC that we would need to do is oh, I'm sorry. So here we need to load uh, let's say b into r0. For simplicity, let's assume that the value and the address are same. Then we are loading other value which is c. So pardon my mistake, I'll correct it. And then R0 and R1 are the registers. We are adding the value in R0 and value in R1 and writing it into another register which is R2. Now the value of R2 needs to be written back to the location which is A. So here again it is given as C. Basically what we are doing in this code is we are adding the values A and B, writing it to C. Okay, now on the CISC, all this can be simply done by one instruction which is add a comma b comma c, where we are getting the data from location A, we are getting the data from location B, both are currently in the memory, residing in the memory. So the processor memory interface will be coming into the picture twice already. When the data is available at the CPU, we add that and we are writing it back to the memory at location C. Okay, so a simple operation has expanded into 4 instructions when we are considering RISC, but in CISC maybe we would be able to do it in 1-2 instructions. That is the primary difference between the RISC and CISC. Here the add operation is performed only on the registers, but here we can perform it directly on some memory locations. So this is how we can assume that internally the instructions would get executed. Each RISC instruction, assembly instruction, would be corresponding to one machine instruction, it will be fetched and executed one by one. But coming to CISC, each machine instruction can be doing multiple things. Like in the previous example, we are getting the value of A, getting the value of B, adding them and writing it to C. So internally, all these actions are split into microcodes, converted them, and we would convert them into micro instructions, and each micro instruction will be executed one at a time. For a little more understanding, I would refer all of you to go through this link. It's a very good informative link about RISC and CISC and how they differ. Moving on, just like the big endian and little endian choice, here there was quite a debate on which type of ISA should we go for. So as early as 1946, Burks, Goldstein, and von Neumann himself have given some hints on what type of ISA we should go for when we want to build a computer. So I'll highlight the points which give us a quick takeaway. The really decisive considerations from the present point of view in selecting a ISA are more of practical nature. One, simplicity of the equipment demanded by the instruction set, and second, the clarity of its application to the actually important problems together with the speed of its handling of those problems. In more simple words, we would decide which ISA to go for based on the simplicity of the hardware that we want to eventually want to run on, and what type of applications do we want to run. If my applications don't need any don't have any complex operations, like say like convolution or anything uh, a multiplication of large numbers and then accumulating them, etc. So those in that cases, even we will be good enough to go with a RISC ISA. So the eventual hardwares what we want and the applications that we want to run on that hardware will give us a hint on whether we have to go for RISC or CISC. So it's basically you can say that it's a difference in the design philosophy. For the same application, we can build a RISC machine and a CISC machine. But if we look at the RISC machine, its assembly code sizes would be much larger, like we saw in the earlier example, and in CISC, the code size would be uh, smaller. In RISC, we can perform arithmetic and logic operations only on registers, whereas in CISC, we can perform on the memory itself. And in RISC, the emphasis is more on the hardware. The hardware needs to, more on the software. The software needs to split any complex operation into a sequence of simpler operations so that they can be run one at a time on the CISC machine. And on the on the RISC machine. And when it comes to the CISC type ISA, the emphasis is more on the hardware, because the hardware now needs to analyze complex instructions, split them into micro instructions, and run them sequentially to get the correct operation. So the software can be more simpler in design. Here the software will do a lot of heavy lifting, but the hardware is simpler. In RISC, most of the transistors that are available are used up for making the registers, and in CISC they are used to store the complex instructions, basically the microcodes and how the mapping um, is maintained, etc. So these are some high level differences between RISC and CISC, and as we go through the next few modules, we'll understand some more differences among them. A few examples of both RISC and CISC. In RISC, we have Alpha ISA, ARC, and other popular is ARM, MEPS, Power Architecture by IBM, then Spark, RISC-V, etc. And in CISC, the most popular would be the AMD and Intel x86 ISS that typically you would find in any of your uh, desktops and laptops. These are so predominant that all the other ISAs are no longer used. Okay, in this course and specifically in this module, we are going to look at RISC type ISA. Why? Because it is very simple and easy to understand what an ISA does by picking a RISC type ISA. And even though RISC and CISC debate is going on from past many years, there is no clear winner. But of late, there has been slight more uh, inclination towards going RISC machines. And in process, we'll pick RISC-V as our example ISA because of late the industry has picked it up, and there are many people who are endorsing it. So a quick take-home assignment for all of you, just to get acquainted with the RISC-V ISA. The rest of this module 1 will be dealing with RISC-V. So there are some links I have provided here for your own interest. The RISC-V has its own web page. You can go through and get a lot of details there. And there's a separate YouTube channel. And one of the videos that I have given here is the roadmap that RISC-V forum has for the next 10 years or so. So the Shakti processor, if you have heard, that's from IIT Madras, is based on RISC-V, and there are a few other good links that I have given here. So go through them. In addition, just to trigger your interest on RISC-V, I'm giving a link about one of the decisions that was made taken by Nvidia almost in the second half of 2016 itself, where they said the CPU within their cards will be RISC-V based. They named it as RISC-V, which is Nvidia RISC-V core. Okay, go through the link to uh, see why RISC-V is more relevant now. With that, I will pause this next lecture. And starting from next lecture onwards, we are going to study RISC-V in more detail. We are going to understand how it was designed and what all are its capabilities, and basically what taking RISC-V as an example and looking at what all aspects the any given ISA will provide us. Okay. Uh, with that, I will pause this lecture. Thank you.